In everyday life, things only tend to move when something's actively repelling them. A plane doesn't fly without the propeller spinning. A car doesn't drive without the engine running. This is because friction is ubiquitous. Friction between an object and a surface tries to make the object stationary with respect to the surface. Air resistance tries to make an object stationary with respect to the air. We'll explicitly model the mechanism behind these forces. A model, which is convenient for quantifying the mechanism behind motion, is to start from the premise that in the absence of forces, an object will move at constant velocity. Indeed, if you do your best to eliminate all forces acting on an object, you will find that it moves with constant velocity. A special case is a stationary object. It will not start moving unless you apply a force. I emphasize that the force-free setting is an abstraction. It is nearly impossible to eliminate all forces. Nonetheless, it provides a convenient framework. As the textbook states, this starting point is codified by Newton's first law. Newton's first law is often stated, an object will remain in a state of rest or uniform motion in a straight line unless it is acted upon by a force. Note the word law. This is short for empirical law. It means that it is a short summary of a series of experimental observations, or rather, in this case, the extrapolation of a series of observations. So what then is a force? Somewhat tautologically, a force is something that makes an object accelerate. Examples we thought quite a bit about in this course already are gravity. An object in freefall accelerates. Ergo, there's a force. This we will understand as a long-range force between the Earth and the object. A second force we've seen is air resistance. This is the force between atoms in the air and an object, which typically slows the object down. It can also speed the object up. Think of hurricanes or tornadoes. It's air resistance which accelerates your roof and flings it into the neighbor's house. The textbook classifies forces in two categories: contact and long range. Long-range forces include gravity and electromagnetic forces. Pretty well every other type of force is a contact force, requiring things to touch. Forces always involve two entities, an agent and an object. I always like to write Fa on B, which corresponds to a force where the agent is A and the object is B. There'll be times when this notation will help clarify our thinking. Note, sometimes it's a little tricky to identify the object. Consider the example in figure 4.3 of the text, where a person is using a rope to pull a box. What is the agent acting on the box? The cleanest way to think of this example is to take the agent to be the rope. Why not take the agent to be the person? Well, the person's not touching the box. So then is it a long-range force? I guess in principle you could take the agent to be the person-rope complex. That'll give you a headache. Take the agent to be the rope. One important feature of forces is they are vectors, and the influence of multiple forces can be calculated by taking the vector sum of the individual forces. If I push horizontally on a box, and someone else pushes vertically in the box, that's going to be completely equivalent to someone pushing diagonally on the box. So, if the force of person A on the box plus the force of person B on the box is equal to the force of person C on the box, then the behavior of the box in this situation is the same as the behavior of the box in that situation. One can simply add up the vector forces.